Performal, formal verification of latency properties for distributed systems.
1 second.
And the speaker is Tony Zhang, co-authors Upamanyu, Sharma, and Manos Kapritsos.
Yes, so thank you for coming to the last talk. I'm Tony Zhang. I'm here to introduce our work Performal, a methodology for using formal verification to reason about the latency properties of distributed systems. And this is joint work with Upamanyu Sharma and Manos Kapritsos. Distributed systems are the backbone of modern applications. We rely on them for critical tasks, from massive computations to the infrastructure services that keep our applications running. Unfortunately, these systems are also notoriously difficult to design and implement correctly. This is due to their scale and their need to handle non-determinism, such as asynchrony, server failures, and unreliable networks. To make these error-prone systems robust, the research community has developed a powerful approach: formal verification. Formal methods are great because they formally prove the correctness of a system to categorically eliminate bugs at compile time. However, most current efforts are dedicated to proving functional safety properties, such as parties in a consensus algorithm never agreeing on different values. We even prove the theoretical concept of liveness, showing that a system eventually makes progress. But none of these techniques help answer the real and practical question, and that is how fast the system performs. This gap is concerning because performance properties, such as latency, are what people actually care about in the real world. Indeed, developers care deeply about how fast their system performs as much as they care about correctness. Companies pour vast resources to maintain the performance requirements of every component in a system. These are typically expressed as service-level objectives. Violating them don't just mean that a website takes an extra second to load. They can actually snowball into major outages. For instance, in 2015, AWS services became unavailable for many hours, and the root cause was that servers exceeded the pre-configured timeout limit for retrieving some metadata. And this triggered a cascade of recovery protocols that overwhelmed the system. Performance bugs like these are not only catastrophic, but are also very widespread. A 2014 study shows that over 22% out of the 3,000 bugs studied are performance bugs. And these are all in very popular systems such as Hadoop, ZooKeeper, and Cassandra. Judging by this prevalence, it is clear that current approaches to prevent such bugs are inadequate. Currently, developers employ two techniques. First is through monitoring and tracing a system in production. This isn't ideal because bugs can only be found after they've already caused problems. Another technique is to benchmark the system before deployment. But just like any testing approach, it is virtually impossible to cover all edge cases, especially in a complex system. In this work, we present a bold new approach to reason about system latency. We ask, can we use verification to prove the latency characteristics of a system and answer questions such as, what is the latency of a request in my state machine replication system, or how long will my system take to recover from a failure? Reasoning formally about latency may at first seem hopeless. After all, our code doesn't run in abstraction, but on a complex mix of software and hardware connected by an unpredictable network. These components all interact to affect latency in ways that are impossible to reason about. For example, how can we possibly prove a bound on execution time if we can't prove how our network or how our CPU performs? And yet, hope remains. Our main contribution is a new abstraction that lets us reason about the duration of distributed executions without being tied to the environment. Our key insight is that latency bugs stem from issues in the code, things such as faulty logic or extraneous loops. And these have nothing to do with how the environment behaves. It is this decoupling of the properties of our code that's within our control from the outside environmental factors that enables formal reasoning about latency. Our new methodology, which we call Performal, uses this decoupling to reason about latency in two distinct tiers. The first tier uses verification to extract a formal guarantee on the worst-case behavior of the system. It uses a new notion of symbolic latency to express the latency of our code without assumptions about the environment. The second tier then embraces the inexactness that's inherent in the environment. It uses the abstract symbolic bounds derived in the first tier to convert fine-grained measurements of local components into an estimated end-to-end latency. So to recap, it is important that we begin to reason formally about the performance of distributed systems. Performal enables latency reasoning by decoupling the code from the environment. Tier 1 produces a rigorous symbolic upper bound for our code, while Tier 2 factors in measurements to make real-time estimates. Now I'll dive deeper into Tier 1 with the central idea of using symbolic latency to make formal arguments about our code. Symbolic latency measures the duration of an execution in abstraction from the environment. Instead of being in units of real time, it is an expression where each term represents certain operations, such as a message delay or a function execution. Consider this example. At time 0, node A runs a procedure send that sends a message to node B. Node B also runs a receive procedure that processes the message. Then, the time that node B finishes processing is given by this expression: the time it takes for node A to run send, plus a message delay, plus the time it takes to run receive. Performal introduces rules for how this symbolic latency evolves as the system executes across multiple nodes. The rules model the passage of time in a distributed system, when hosts perform actions such as sends, receives, and timeouts. Finally, we prove formal bounds on the latency of events by proving how symbolic latency of the system evolves according to these rules. Let's see how this works in practice. We begin by modeling our system as a state transition system, similar to the model used in Ironfleet. In this work, we do our implementation and proofs in the Daphne language. Each host is modeled as a state machine that's possibly infinite. They start from some initial state and takes a sequence of atomic transitions. The system state is simply a collection of all of these host states, together with a set of messages that represent the network. Every transition of the whole system then corresponds to one local step of a host, which may possibly update the network. In Performal, we extend the state machine to reason about the timing of events. This is through associating each host and message with a timestamp. These are a ghost state that are used only for proofs and are not compiled into the executable. During the execution, a node's timestamp is a symbolic latency expression representing the time it took for the node to reach its current state, while a message's timestamp captures the delivery time to its destination. After writing down our system, we now specify what we want to prove. Here, our top-level spec is a state predicate that asserts the boundedness of our timestamps. For instance, if a client sends a request message at time 0 and then gets a response, the timestamp of the response message is at most some expression. We want to prove that this predicate is an invariant of the system. It is interesting to note that how a user comes up with these latency specifications may be quite different from traditional safety specs. Here, we may not know at first what is the bound we want to prove. Instead, we only know the initial state and a target event whose timestamp we want to bound. We discover that final bound by starting at the initial state and proving invariance on the timestamps of an increasingly wider horizon of events. This is best viewed as a line of dominoes. The bound on one event induces a bound on a subsequent line of events. Here, we know that the client sends the request at time 0, and that's our first domino tipping over. The first domino falling implies that the second domino falls next. The server receives the request after some message delay D. As a result, the server finishes processing after some additional time P. And finally, this means that the client must get the response after 2 message delays plus P. Altogether, we see that the process of proving latency properties helps us understand the system. It gives insights into why the system behaves like it does and what we can do to improve it. Now, let's see how these timestamp rules work in a concrete example. Our example system has nodes in a ring configuration. Every node is identified by an ID that is its position in the ring. Initially, node 0 holds the token. Any node holding the token grants it to its successor, and other nodes wait to accept the token. Eventually, we complete a full circuit, and we want to reason about how long this circuit takes. In the initial state, every node's timestamp is 0, and there are no messages in the network. Let node 0 now take the first step by sending a message that grants its token. By our send rule for updating timestamps, node 0's timestamp advances by a term denoting the time it took to execute this grant operation. Meanwhile, the message is assigned a timestamp at when it was sent, plus a message delay. This indicates the latest time the message will arrive at node 1. Next, node 1 accepts the token. By the receive rule, node 1 is updated to the max between its local timestamp and the incoming message, plus the time it takes to run this accept procedure. Fast forward, and node 1 passes the token to node 2. By the send rule, node 1's timestamp now increases by a single grant term. The message sent by node 1 gets node 1's timestamp plus a delay, and node 2 receiving the message by the receive rule gets the following. Now, this generalizes into the following invariants that we prove. We see that for each in-flight message, its timestamp is related to the sender's position, like so. As a consequence, each node holding the token has this bound, its position multiplied by the sum of grant, accept, and delay. And overall, for our top-level spec, we prove that the time it takes to complete the full circuit is this, the size of the ring multiplied by this sum. And this concludes how we derive and prove our bounds on circuit time. The abstract bounds of Tier 1 are useful for identifying latency bugs, when the bound we end up deriving is larger than expected. The proof process also helps highlight the root causes of these bugs. In fact, we used this process to identify a real bug in Apache ZooKeeper, and the details for that are in our paper. In practice, however, there are cases where we want to go beyond just a symbolic bound and want a real-time estimate, such as when we're setting our SLOs. And this is where Tier 2 comes in. It is a technique to convert the symbolic bound into a concrete real-time estimate. In Tier 2, we treat a symbolic bound as a formally derived recipe for computing an end-to-end estimate using just local measurements. Suppose this is the expression that we proved in Tier 1. First, we measure each individual component in some target environment. This gives us their empirical distributions representing the likelihood of the component executing within some amount of time. Then, we treat each term as independent random variables. And finally, we can compose these component distributions into an end-to-end estimate according to our expression. This is done using standard rules of probability, and in this case, we get an upper bound on how long these three components take to execute in sequence. To evaluate this technique, we applied it to our token ring example. We measured the component distributions of our grant, accept, and delay steps, and estimated the final circuit time using those measurements. For a ring of size 10 and across a series of artificial workloads, Performal estimates that the latency should behave like so. And here's the actual observed latency for comparison. And we see that the estimates track the actual latency very well. Of course, this token ring is an extremely simple system. So beyond this, we evaluated much more complex systems, such as a state machine replication library that's built on top of Paxos. And here we see that the results are similarly accurate. So in summary, I discussed the Performal methodology for reasoning about the latency of distributed systems. The key insight is that we decouple the code from the environment using rules to symbolically reason about latency at the code level. The workflow begins by modeling our system as a state machine. Next, we specify and prove a symbolic bound of a target event. And finally, we can use that bound as a recipe to produce an estimate of the real-time latency of the system through just doing some local measurements. There's much more details in our paper. For instance, we formally state our timestamp semantics and show how we apply them to great success to complex systems such as Paxos and ZooKeeper. And finally, we also evaluate our real-time estimates on all kinds of execution environments, including geo-distributed clusters on AWS. And to end off, we believe this work is the first step in a new direction towards reasoning formally about system performance, and we hope it will inspire future work in this area. With that, I'm happy to take questions.
John Sharma, when you described your token ring example, then you were assuming that each node was able to process its message as soon as it arrived, if I understood it correctly.
Yes.
But if you have a server that is serving multiple clients, then of course the server might be busy at that point.
Yes.
And I'm curious in particular about overload situations, which might be situations that could lead to very long, unexpectedly long latency.
Right.
How do they fit into this framework?
Good question. So we do. So in the presentation, I skipped over some of the more specific details that's available in our paper, but we do reason about how queuing delay might affect how soon a node is able to process a message when it arrives. So when there are multiple messages in the network, we do reason about how those messages could be queued ahead of the one incoming and cause a delay in that. And however, one thing I would want to note is that we are reasoning about systems in the case where throughput is not the bottleneck. So we're reasoning about the system when there's just one ongoing request in the system, and all the messages that are currently in the network are in service of that one single request.
Hi, so I'm Constantin Enea from Ecole Polytechnique. So I was wondering, like in your example, all messages were causally related. So what happens now when you have non-determinism, like either because you have concurrent sends or because you, for instance, wait for messages until a timeout expires or things like this? So how this?
Yeah, good question. So again, the token ring example that I showed is a simple system. It has just one single execution path. But again, so for instance, we also did this for like a Paxos state machine replication system. And so what happens in that case is that a node would have to wait for a quorum of messages to arrive before it takes any action. And we do account for that, and we have rules to account for that, yeah.
But in principle, you have like some max or mean.
Yes, that is right. So we have a rule that takes a max when you have like different execution paths.
Hi. So if you're applied to this framework to existing frameworks proving safety properties, would it be possible to do that in a modular manner, especially in terms of writing down the invariants and actually performing the proofs?
I'm sorry, I'm not quite sure what you mean by what manner, sorry?
In a modular manner, so like say you have a safety invariant, so say you have to prove for some safety property and you'll have an invariant there and a proof script there. If you try to apply this framework, like will you need to rewrite the whole invariant again and the whole proof script again, or would that be possible to do it separately? Right.
So we can actually write our proofs modularly. So first of all, these performance proofs are just safety proofs. And we can do it modularly in this way. So we can actually split our like a distributed protocol into different phases, and then we can prove the bound on each phase individually, and then we can just stitch them together. So for example, in Paxos, there's like phase 1 and phase 2. We can prove each phase to give a bound for like just executing that, and then we can put them together to see what happens when they execute in sequence. And then if we were to like do a modification in one of the phases, we only have to change the proof for that particular component.
Okay, I had another small question. So
yeah.
You mentioned that a key part was that you decouple the code from the actual environment by abstracting through an abstract timestamp.
Yeah.
Would that approach be able to apply to other systems? Say if you want to approve latency bound for an operating system, or would that be hard because it is more tightly coupled to say the CPU?
Yeah. So I would say it might be harder because I agree like it would be more tightly coupled to the CPU. I have to think more about how it works, yeah.
Thank you.
All right, let's thank Tony again, and that concludes our session.